So what we saw is, whatever the case, field is always radially outward. Field is always radially outward. And now second thing, we have to understand the second thing. Since this is an infinite wire, we took this piece and another piece like this, P1 and P2, and try to find this electric field at this point P. At the next time when we take P here, new point P, again we don't need to consider these small length elements. We will consider, since this is an infinite wire, we will consider length element accordingly here and here. So the position of P on this y-axis also does not matter. Position of P on the y-axis does also not matter, because as we shift P from here to here, these elements will also shift from here to here. Okay, so what I said is that if point P is shifted from here to here, so the elements which were, let us say, here and another element was here, so they will also shift from here and here, so they will also shift. Okay, so the position of P does not matter, as well as the direction. So in the first case we saw that if we rotate this point, it will create a circle. In the next time, if we move P, if we move this circle in the y direction, what will it create? It will create a cylinder. See, now this is a cylindrical surface. So first a circle of radius r, and let us move L length. So this will be a cylinder of length L and radius r. So the outside surface will be a cylinder for this wire. Now we have to calculate electric field E at point P, which is r distance from this wire, and we have made a cylinder of length L. So these are the considerations. Okay, now what is the direction of this electric field? This electric field is always radially outwards and normal to the surface of this cylinder everywhere. Here it is also normal, at this side it is always normal to the surface. And you also know that the normal to the surface also radially outwards. So both these, electric field and normal to the surface, are pointing in the same direction. That means cos theta is equal to cos 0, that means 1. So in that case, E dot delta S in each and every case is simply E delta S. Okay, so E delta S. So what I tried to say is, if you want to calculate electric field due to a point P which is outside this wire, first you rotate it and make a circle. So you see that whether this point P is here, it does not make any difference. Second thing is, if you move this P anywhere along this y-axis, that again does not make any difference. So you move it along y-axis L length. So ultimately you get a cylinder which has a length L and radius r. In each and every case, electric field is always outwards, and normal of the surface is also outward in each and every case. Hence E dot delta S is always E dot dot is cancelled because cos theta is 0, cos 0 that means 1. So it is always E delta S. So this is the whole story till now. So now let us see what has happened. So now flux through the Gaussian surface. So what is our Gaussian surface? This cylinder is our Gaussian surface. This cylinder is our Gaussian surface. And how much charge is enclosed by this Gaussian surface? See, the linear charge density lambda was delta Q by delta L. Now the length of this element is L. Total length of this element is L. So total charge enclosed, this was simply lambda delta L, and now the total charge enclosed Q is simply lambda into length L. This is simply lambda L. So the total charge enclosed by this Gaussian surface is lambda L. Lambda L. Now, so flux through the Gaussian surface. So flux through the Gaussian surface phi, you know, is E dot delta S. Okay, and you saw that there was no dependence on this angle, and cos theta was 0. So that was simply E delta S. Now this is E, and the surface area of cylinder is 2 pi RL. E is there, delta S, surface area of a cylinder is 2 pi RL. So this is there. So this is phi, this is phi. The surface includes charge equal to lambda L, as I just explained that charge enclosed by the surface is lambda L. And putting it in the Gauss law. What is Gauss law? Phi is equal to E dot delta S is equal to charge enclosed divided by epsilon naught. So this is Gauss law. Now this is E delta S is E into 2 pi RL, the surface area of the cylinder, charge enclosed lambda L upon epsilon naught. Now this is the whole thing. Let us solve this. E is equal to simply L and L cancels out, lambda upon 2 pi epsilon naught R. 2 pi epsilon naught R. So one important thing which you can see here, for a uniformly conducting wire, field varies as 1 by R. For a uniformly conducting wire, field varies as 1 by R. So electric field previously for a charge was 1 by R square. For a dipole it was 1 by R cube, and for a long wire it is simply 1 by R. It is simply 1 by R. So that is the difference, and we found it using simply the Gauss law. Let us understand some of the things here what are written here. So the where n is the radial unit vector. What is radial unit vector? Here you can see in each and every case it is always radially outward. That is the same. They are saying n vector is the vector, unit vector, which has a direction radially outwards. Okay, and you found the magnitude that electric field is simply lambda upon 2 pi epsilon naught R. 2 pi epsilon naught R. So here we don't have charge but lambda, and E varies as 1 by R. So n is a radial unit vector which in the plane normal to wire passing through the point E. So E is directed outwards if lambda is positive and inward if lambda is negative. So what they are trying to say, if we have solved for positive charges, this was positive, so direction was always outward. But what would if we had negative charges? So for negative charges, so the direction would be inward. So that is what they are trying to say here.